We'll introduce spontaneity of the processes. Okay. First, we'll discuss about neutralization, enthalpy of neutralization. Very, very important concept. Delta H naught N neutralization. This is in this enthalpy of neutralization. 1 mole of undissociated water is formed. It is a liquid from its constituent respective ions from monoprotoic acids and bases, or from its dilute solutions, that is from H plus, this is aqueous plus, and OH minus aqueous. Okay, here 1 mole of undissociated water is formed from its constituent ions H plus and OH minus from dilute solutions. Here there is a certain change in their enthalpy, that is always constant of 57.1 kilojoules or minus 13.7 kilocalories, because 1 calorie value we know 4.18, substituted there, we'll get the answer. Now here this H plus ions from monoprotoic strong acid is reacted with here monoacidic base, strong base gives salt solution plus here water is formed, H2O. While forming this undissociated water, there is a change in their enthalpy, that is neutralization, that is always constant, 57.1 kilojoules. This is always constant value. When monoprotoic strong acid like HCl or HNO3 reacted with monoacidic strong base like NaOH or KOH, this is. Now it is in aqueous medium, it is also aqueous medium, that is from dilute solutions, meaning also it is aqueous, it is also aqueous. It is a strong acid and it is a strong base. Strong acid and strong base always react with each other against salt is there NaCl plus water is formed. Here KNO3 plus H2O water is formed, undissociated. Now always constant, either in this case, delta H naught N must be equal to minus 57.1 kilojoules. Strong acid, monoprotoic strong acid and strong bases, they are monoacidic strong bases, neutralizes. I'll take again this example. In aqueous medium, it is H plus aqueous plus Cl minus aqueous plus Na plus aqueous plus OH minus aqueous gives NaCl in aqueous medium also ionizes, it gives Na plus aqueous plus Cl minus aqueous, but here water is a weak electrolyte, cannot dissociate it completely. So before the reaction and after the reaction, your H plus and Cl minus, Na plus, OH minus all are in ionic state. But in product side, Na plus and Cl minus, water is undissociated. Now here before and after chemical reaction, Na plus and Cl minus, here Na plus and Cl minus ions are called a spectator ions. These are spectator ions. Your Cl minus, Na plus and Na plus, because they are in ionic state, in a dissolved state, ions get cancelled. Finally, 1 mole of aqueous plus 1 mole of aqueous OH minus and H plus gives undissociated water, H2O liquid. Now that is delta H naught N is equals to always constant, that is 57.1 kilojoules per mole. This is fixed. Not only HCl and NaOH, your HNO3 KOH, like any monoprotic strong acid and monoacidic strong base, neutralize, react with each other, it gives always 1 mole of undissociated water. Liberated value is always constant. But in case of strong acid and a weak base, gives salt plus water, and here the weak acid and a strong base also gives salt plus water. Here the weak acid and a weak base also gives here the salt plus water. In all the three cases, the liberated value, this is a weak condition, liberated value delta H naught N is less than 57.1 kilojoules. This is a very, very important relation. Why it is less than 57.1 kilojoules in these three cases means strong acid and weak. Here weak cannot ionize completely as strong base, here NaOH. Now here weak acid cannot ionize completely as like HCl. Strong base ionizes. Both are weak, cannot ionize completely. It doesn't produce accurately 1 mole of water molecule. That's why to ionize completely, the liberated 57.1 kilojoules amount of energy among the some amount of heat required to ionize completely either a weak acid or the weak base for neutralization. That's why always less than 57.1 kilojoules. For example, I'll take one simple example for this. Strong acid is HCl, weak base is NH4OH. It is completely ionizes H plus plus Cl minus. But to ionize this, here NH4 plus OH minus between, it is a weak, cannot ionize completely. To ionize this in aqueous medium, the liberated amount of heat in strong acid and strong base medium, some amount of heat is utilized, liberated heat is utilized by this weak base. Either weak base or weak acid or anyone, weak electrolyte utilizes some amount of heat liberated in this process. That's why always less than. How much heat is required to calculate? That means here heat required is, how much heat required for that is 57.1 minus amount of heat liberated in weak condition. In weak condition or the neutralization. This is the formula to calculate how much amount of heat required to ionize weak electrolytes. So, very, very important concept this is. Enthalpy of neutralization. Here, change in enthalpy occurs when 1 mole of undissociated water molecule is formed from its dilute solutions when monoprotic strong acid and strong base completely neutralize. It gives salt plus water. Always liberated value is constant. This is, but whereas in these three cases it is not constant. Reason explained. Reason is, here to ionize the weak acid or the weak base, some amount of heat is required to ionize completely into its constituent ions. That's why under this weak condition, heat of neutralization is less than 57.1 kilojoules. Okay, clear. So after this heat of neutralization, here two important laws are there. I'll explain these two important laws. Laws of thermochemistry. Laws of thermochemistry. Just like laws of thermodynamics, here laws of thermochemistry. First one is first law of thermochemistry. This is also called Laplace-Levaizer's law. Laplace-Levaizer's law. This is already explained in previous class, like some important enthalpy of reactions. Some important features of enthalpy of reaction, this point indirectly explained. According to this, when a chemical reaction takes place, during a chemical reaction takes place, amount of heat is, for example, liberated. Amount of heat is liberated means your delta H is equals to negative. This is reaction, standard condition. For example, amount of heat is absorbed, means your delta H naught R is equals to positive. So the A gives to B. Now this is considered as an exothermic reaction. Exothermic. It is a forward reaction. In this forward reaction, amount of heat is liberated. That's why it is an exothermic reaction. When the same reaction is reversed, B gives to A. Now the delta H value is equals to positive, endothermic. For this, I'll give C plus O2 gives CO2. Delta H R is equals to minus 393.5 kilojoules. When it is reversed, CO2 gives C plus O2. Then delta H naught R is equals to plus 393.5 kilojoules per mole. So by using this, Laplace-Levaizer stated an important statement. In a thermochemical reaction, amount of it is liberated or absorbed. When the reaction is reversed, the magnitude of delta H is the same, but the sign of this delta H is changed. So here magnitude is 393 or 393. Same chemical reaction, formation of CO2 or the reaction of CO2. When it is reversed, CO2 to C plus O2, it gives plus 393. Means here heat, what happens, required. Heat required means heat is absorbed. Hence it is an endothermic reaction. But here heat is liberated. That's why it is an exothermic reaction. The same concept explained by Laplace-Leveisser. That's why it is called a first law of thermochemistry. Okay, next, second law of thermochemistry. Here, second law of thermochemistry. This second law of thermochemistry is also called Hess law of heat of summation. SUMM, not SOM, summation. It was introduced by scientist Hess law. According to this Hess law, when a chemical reaction takes place in a single step or in multiple steps, the amount of heat is liberated or absorbed remains constant, same. For this, I'll give a simple example. Direct step or a single step in this, the C plus O2 gives CO2, carbon dioxide. It is a solid gas and it is also a gas. Delta H naught C combustion or the reaction whatever at minus 393.5 kilojoules per mole. Multiple steps. In multiple steps, step one is, first one is carbon combines with half O2 gas, it gives CO gas, carbon monoxide, delta H1 in first step, minus 285 kilojoules per mole. In second step, the obtained carbon monoxide gas again react with the half O2 gas. It gives CO2 gas. Now delta H2 is equals to minus 110.5 kilojoules per mole. From equations 1 and 2, step 1 and 2, according to thermochemical equation, reactions are added, multiply or divided. Here equation 1 plus equation 2, step 1, step 2, by adding this. Here CO get cancelled. C plus half O2, that is O2, it is a solid and gas, gives CO2 gas. Now final enthalpy of a reaction or the formation or the combustion is equals to, here combustion given, but you take combustion, delta H1 plus delta H2. Now here this value is minus 285, minus of plus minus 110.5, that is minus 385.5 kilojoules per mole. See here. According to the second law of thermochemistry, Hess law of heat of summation, when the process takes place in a single direct step, amount of heat liberated is minus 393.5 kilojoules. You are liberated. In some other examples, may be absorbed. The same chemical reaction is carried out in a multiple steps. Here are 2 steps required to calculate that. In single step, that is in step 1, minus 285 kilojoules heat liberated. In second step, minus 110.5 kilojoules liberated. Sum of these two, it gives enthalpy of combustion or the reaction or the formation of CO2 is minus 285 minus 110.5. Here finally we'll get minus 385.5 kilojoules per mole. Okay. So by using this, here are some important conclusions of Hess law of heat of summation. So in objective, which of the following is true or false? Maybe we'll ask according to this. According to this Hess law of heat of summation, in thermochemical reactions may be added or multiply or divided, and here enthalpy of reaction depends on bond energies of reactant minus bond energies of products. And also this enthalpy of reaction depends on summation of enthalpy of formation of product minus summation of enthalpy of formation of reactants. Yesterday given these two important reactions. But the thermochemical equation is independent on how the reaction takes place. Didn't explain its rate. In chemical kinetics, we know rate of the reaction, speed or the velocity, but this is not given about the rate or the manner or the path how it takes place. Only it explains how to determine this. And also applications of Hess law. By using Hess law, we can calculate applications. We can calculate lattice energy by Boron-Haber cycle. Also, it is used to calculate the resonance energy of the molecule system. So, by using Hess law, here lattice energy of the system we can calculate by using Boron-Haber cycle, by using these multiple steps, and also resonance energy. Some important applications and conclusions of Hess law of constant heat of summation. This is under laws of thermochemistry. Clear? Okay. Then most important concept after this. One remaining balance, an important concept of, is there. That is always while doing problems we can use enthalpy of combustion. Last point. See, enthalpy of combustion, last one. This is standard enthalpy of combustion. C. 1 mole of compound is 1 mole of compound, any compound or element is completely burned in excess amount of oxygen against respective compounds plus heat is liberated. That's why minus Q kilojoules. So the amount of heat is liberated. Always these enthalpy of combustion reactions are always exothermic. Amount of it is liberated. Its definition is amount of it is liberated when 1 mole of compound is completely burned in excess amount of oxygen with the respective compounds. Why I am introduced here in this final concept means regular in biological system we can use this simple enthalpy of combustion. Biological processes means in a living system in our body, your glucose, the C6H12O6 completely burns an excess amount of oxygen and gives corresponding compounds means carbon dioxide plus water, then delta H is equals to amount of it is liberated. While playing cricket or while playing any one game, some amount of energy required, the required amount of energy is available under the name of glycogen. Here a glycogen present under the muscles. Wherever amount of energy required, by using excess amount of oxygen, here this is carbohydrates completely converted into carbon dioxide and water, amount of it is liberated. Okay. Here balancing, here always one only, no need to change this number of moles, 1 mole. Here excess means we can change here. Carbon atoms 6 are there, better you take 6 carbon atoms. Your hydrogen 12 are there, that's why take here the 6. Now carbon hydrogen balanced, remaining is oxygen. Here 12 and here the 6, total 18 oxygen atoms are there. Here already 6 are there, we want 12. That's why I take here the 6. 6 2 is to 12. Here already 6 are there, total 18 oxygen balanced. So 1 mole of compound is completely burned in excess amount of oxygen, it gives corresponding carbon dioxide and water. This is complete combustion. In organic chemistry, we'll get 3 cases: complete combustion, partial oxidation, incomplete oxidation, incomplete combustion. 3 cases are very, very important. But in this case, complete combustion takes place, carbon dioxide and water produced, amount of it is liberated. Here, based on this, we can calculate the calorific value of food or of fuels. Calorific value means how much amount of food or the fuel burns, how much amount of heat is liberated. For example, here carbon plus oxygen against carbon dioxide. Now that value is minus 393.5 kilojoules per mole. Its calorific value is nothing but delta H naught C divided by weight of the substance. Weight of the substance. Here in this process, by complete combustion of carbon, how much amount of it is liberated? 393.5. And here weight of the substance means here carbon weight, that is atomic weight, 12 grams. Take divided by 12 grams. This is the kilojoules. So finally here the calorific value units are kilojoules per gram, kilocalories per gram. Kilocalories per gram we can take. This is the unit of calorific value. Calculate like this. So not only this carbon plus oxygen is carbon dioxide, any food material like here we can take CF is equals to calorific CV, calorific value is equals to in this delta H naught C divided by, in this case 180 grams, because here C6 H12O6, 12 into 6 plus 12 into 1 plus 16 into 6 will get a 180 molecular mass of the substance or weight of the substance given. Now this value is equals to LU minus Q divided by 180. That is the calorific value of any food or fuels. This is the story about thermochemistry part. In thermochemistry and thermodynamics, one of the most important law introduced, that is zeroth law and first law of thermodynamics. What is first law of thermodynamics? First law of thermodynamics. According to that, energy neither be created nor be destroyed. but one form of energy can be converted into another form. Here, first law of thermodynamics. So according to this first law of thermodynamics, just energy neither be created nor be destroyed, but one form of energy can be converted into another form. This is first law of thermodynamics. Here, first law of thermodynamics didn't explain how the process takes place, that is the manner of the reaction. So the fails to explain manner means how the process takes place, and also feasibility of the process. Next one is fails to explain extent of the reaction or the process. So after thermodynamics and thermochemistry, there is a problem arise to explain how the process takes place. Are the processes feasible or not? Is it possible or not? Then fails to explain extent of the reaction. To explain for all these, another important law is introduced, that is second law of thermodynamics. In this second law of thermodynamics, most important number of statements are there before that. Before the statement of second law of thermodynamics. This second law of thermodynamics is useful to explain how the reaction takes place. Is it possible or not? Here the reaction is spontaneously takes place or not, and how much completed, the extent of the chemical reaction explained clearly. So to explain the statement of second law of thermodynamics, we want first spontaneity. Spontaneity is a plural word. Here it contains both spontaneous and non-spontaneous. Spontaneous and non-spontaneous processes. This is the last concept in thermodynamics, spontaneity. What is a spontaneous process? What is a non-spontaneous process? What are the factors responsible to explain the spontaneity of the reaction? Overall spontaneity to explain, overall complete here H required, enthalpy required, S entropy required, and G free energy required. It is the heat factor, enthalpy factor, free energy factor. So here by using one by one enthalpy factor and entropy factor and energy factor, we can decide spontaneity of the reaction. Final conclusion is delta G is equals to negative, that is a spontaneous. Delta G is equals to positive, that is a non-spontaneous process. Delta G is equals to 0, that is equilibrium process. The process is at equilibrium. But initially, direct G we don't know. Initially, with the help of H introduced spontaneity. First here, what is a spontaneous process? What is a non-spontaneous process? And in what way process takes place? First we'll discuss about spontaneity. Spontaneous and non-spontaneous process. spontaneous process. Takes place by itself without any assistance or aid or help. By itself, a process takes place by itself without any assistance, aid or help, external work. Without any external work, such processes are called spontaneous processes. For example, in a chemistry class, while writing chemistry notes, this is the table. Students are generally in chemistry class, they are all in sleepy mode. While writing, people while writing something by using pen, they are in a sleepy mode. Yeah, the pen or eraser or whatever it immediately on the table to the earth. This is or on floor. This is the pen, for example. This pen just fall on earth. This is a pen here. This is okay. In chemistry class, like happened like regularly, because students all are feel something bore. So here they, while writing chemistry notes, suddenly this pen from table to the earth, this is the higher level. Higher level, this is the lower level. Lower level. So here the pen from higher level to the lower level, from table to the earth, no need any external assistance or help or any other external work. Itself comes from higher level to the lower level. At a higher level, pen has highest potential energy P. Highest potential energy means are the minimum stability. Whereas the pen at a lower level has less potential energy, P, maximum stability. So moreover, here pen try to reach the lower level and try to reach the less energy state to attain the maximum stability. So what happens here? Higher level to the lower level, energy what happens? Decreases, because at higher level energy is more, potential energy is more, clear? But at lower level energy is less. Higher level means initial state here H1. Lower level means here the final state, it is H2. If it is a process, chemical process, reactants and products. Now the difference is delta H is equals to your H2 minus H1 or HP minus HR. Now this is generally your HP is less than HR. Reactants energy is more than compared to the products. That's why this value is more. Finally, we'll get the negative. When delta H is equals to negative, that is generally considered as a spontaneous, because spontaneous process is a process which takes place by itself without any external assistance, aid, help or external work. Your pen without any, just initiation required here. Initiation help required. Your initiation help required means student do that starting by using he or she, just means from higher level to the lower level to drop this, just left this pen and immediately falls from higher level to the lower level. Higher energy state comes to the lower energy without any external aid. What happens in this process? Energy decreases. It is an exothermic reaction. Okay. So by using this, thermochemically initially stated any process, in any process, amount of energy is liberated, that is the exothermic process. In such cases, all processes are considered as spontaneous. But after this technical information, some people are raising some important questions. That is, water, take a cup of water. Here, this is the water H2O exposed to the atmospheric air. It is a liquid at a constant pressure. After a certain time, the level of water, what happens? Decreases. How the water level decreases from air to air? Water level decreases by absorbing the atmospheric temperature and pressure. Some amount of water by itself evaporated. Water level decreases. To evaporate the water here, what is the main here temperature required? What happens here? Heat is absorbed. Heat is absorbed. Heat is absorbed means delta H is equals to positive. It is an endothermic reaction. But initially, spontaneous means without any external aid. Energy decreases. Then there are the exothermic process. All exothermic processes are the spontaneous. But by using this example, also are the ice cubes, are the H2O solid exposed to the atmospheric air. Fusion takes place, just melts here, then slowly gives H2O liquid without any external aid. Ice exposed to the atmospheric air in a summer season slowly melts and converted into liquid. Here heat absorbed by the atmosphere. It is also a endothermic process, also a spontaneous. That's why by using only exothermic process, we can't decide the process is spontaneous or non-spontaneous, because there is a criteria to explain spontaneity. Not only exothermic, endothermic also some are. Some exothermic reactions like C plus O2 gas, CO2 gas. Now delta H is equals to minus 393.5 kilojoules liberated. Exothermic spontaneous. But it is help required, assistance. That is help is only initial help required, initiation required. For what purpose? For heating. So heat this carbon and oxygen, initiation required. After initiation, itself takes place without any external aid. That's why it is also an exothermic process. So by using only delta H is equals to negative, we can't decide its spontaneity. Either it is spontaneous or not. So generally, delta H is equals negative spontaneous, delta H is equals to positive non-spontaneous. If you can imagine, like, it is not true in all cases, because here evaporation of water and melting of ice, even though they are endothermic, they are the spontaneous. It is also a spontaneous. By using this, delta H is positive non-spontaneous. But by using this, it is a spontaneous. That's why we can't decide its spontaneity or the spontaneous or non-spontaneous by using only delta H. We want one more important factor, that is called a disorder factor. Randomness, measure of disorder, measure of randomness, that is called a entropy factor. If you know the entropy factor, then easy to explain spontaneity of a chemical process. Spontaneous by itself without any external help. Non-spontaneous. Your external aid or help, external work required. External help or the work required. A process which takes place by external aid or external assistance or external work is called a non-spontaneous process. See it? From my hand, chalk comes from a higher level to the lower level. No need any external help. We want assistance to fingers required. That is your spontaneous process. The same chalk from lower hand to the upper level, like to throw it continuously, my hand energy required, that is lower level to the higher level, amount of energy required. Here water comes from overhead tank to the bucket. By just on the tap, water will get it without any external aid. But to pump the water from ground level to the overhead tank continuously, what do you want? Electrical motor required. So water comes from higher level to the lower level, spontaneous without any external aid, general physical process. But here non-spontaneous means water from ground level to the overhead tank, here continuously electrical motor required. That is a non-spontaneous process. To explain this, your delta H only is not suitable to explain spontaneity. We want one more important factor, that is randomness or disorder of the system. Measure of disorder, that is called a entropy. Okay? Tomorrow we'll discuss about this entropy and everything. We'll finish in next session, that is Monday. We'll complete the maximum this. Before that, delta H only is not suitable. For this final conclusion, delta H is equals to negative, spontaneous separately if the loss, and here delta H is equals to positive, that is non-spontaneous. Graphically, how we can express this? Is the graphical representation between potential energy along y-axis and reaction coordination along x-axis. This is the potential energy of the reactants, that is maybe HR. Now to get the negative value here, HP is less than HR. Here reactant value is more than compared to the products. That's why for this graph we can take like this. This is the enthalpy of the reactants, HR. This is the enthalpy of the products. Now this is the difference between enthalpies of the reactants and products, delta H. Now this is formula we know, HP minus HR. See here? Here energy 0, 1, 2, 3, 4 calories. See here? Product value is less than compared to the reactants. That's why here HP value is less than HR. That's why this values will get it a negative value. That's why it is an exothermic reaction. This is the graphical representation for spontaneous of exothermic reaction. Similarly, for endothermic reaction, a graph is plotted between same potential energy and reaction coordination. Now this is the same here HR, but to get a positive value, your HP is greater than HR. That's why your curve is like this. Now this is the reactant value, this is the product value. This is the difference. Delta H is equals to positive value. that is HP minus HR. Now here the HP is greater than HR, then we'll get the positive value. Here the 0, 1, 2, 3. Product value is more. This is the HP value is more. 3 minus 1 will get to 1, positive value. That's why it is endothermic reaction graphical representation. Okay, these are the two important graphical representations for exothermic and endothermic reactions. This delta H only is not suited to explain the spontaneous or non-spontaneous spontaneity of the process. One more important factor required, entropy. In next section, I will complete this entropy, and I will cover the about Z last concept, and I will cover the maximum previous year questions. Will complete in next section. Okay, take care.